In this short video, we're going to talk about something actually quite simple, rings of polynomials. So let R be a ring, then R bracket X, or sometimes I'll say R adjoint X, is the ring of polynomials in X whose coefficients belong to R. And then the ring operation of addition and multiplication are the same as in high school algebra. So again, a polynomial like P, let's call it P of X, is powers of X added together with some coefficients or elements of R. Usually in high school they're numbers, but A0, A1, and AN, they all belong to our ring. For example, R could be the ring of integers or the rational numbers. So you can think of the AIs as numbers intuitively. And then X is the variable. And maybe in high school algebra we start off with writing the highest degree coefficient first, or highest degree term first, and that's also allowed. I just didn't do it this way. Here I started with the constant term and then followed by the linear term and so on. But you could also write this starting from this term and descending degree. The addition is commutative. Now if the ring is commutative, then the addition and the multiplication are commutative, and then R adjoint X is a commutative ring. I'll usually be thinking that working in this case where R is commutative. If R has 1 as the unit, which is what rings with unit have, then R adjoint X has 1 as the unit, considered as the constant polynomial. This is again a very obvious statement here. Okay, and then just a piece of terminology. If we have a polynomial where the highest degree term is n, this a sub n is non-zero, so that means the x sub n is actually appearing, or has to appear. Then this this number n is called the degree of p of x. So just familiar from hopefully high school algebra, the degree of a polynomial. Another thing that's quite simple, but has some unfortunately fancy terminology, or sounds complicated, is this evaluation homomorphism. So let R and S be commutative rings, and suppose we have an element lowercase s in this ring S, and suppose we have an ring homomorphism I from R to S. You can think of R as being a particular example is when R is a subset of S, or a subring, I should say, of S. And then the simple fact is that there's a unique ring homomorphism phi of S. Now this S here is this lowercase s that goes from this ring of polynomials to this ring S that extends our ring homomorphism R to S, and such that phi of sub phi S of X is equal to X. This is a mouthful, but it's actually quite simple. All it's saying is, if you give me a polynomial, so an element of R adjoint X, all I'm going to do is wherever there's an X, substitute it with S. So here I have X, so that becomes S. X to the n becomes S to the n, and so on. And then the A0, A1, and AN, they're in R. We want them to land inside S, and sometimes this is just an inclusion. R is naturally a subring of S, but it doesn't have to be. And then you just send the coefficients A0, A1, AN into S by this map. We'll do an example on the next slide. But the reason this is called an evaluation homomorphism is just because we're evaluating this polynomial at X is equal to this lowercase s. We're evaluating or substituting X for X, we're substituting S. So here's a simple example of an evaluation homomorphism. So let I be the natural map from the integers to the integers mod 5, be given by sending an integer n to n mod 5. So 1 goes to 1, 2 goes to 2, and so forth, and then 5 has to go to 5 mod 5, which is 0, and so forth. Anyway, let's pick this evaluation at s equals 3, or evaluation at 3. So we're picking a number in this target ring. 0, 1, 2, 3, 4 are our choices. I'm just going ahead and pick 3. And so then this phi sub 3 is the homomorphism from the ring of polynomials with integer coefficients to Z5, and it has to send x to 3. That's just what I just chose as a specific example. I can choose other ring homomorphism that sends x to 4 or any other number in Z5. Okay, and then because this is a ring homomorphism, x times x, or x squared, has to go to 3 squared, and then x squared plus 1 has to go to 3 squared plus 1. Again, that's because we're insisting on phi of 3 being a ring homomorphism, and so it preserves or respects addition and respects the multiplication. So once you tell me where x has to go, everything else is forced. So what about things that don't involve x, like 7? Well, another property of this homomorphism phi sub 3 is that it extends the given homomorphism I. So 7 belongs originally in Z, and I sends Z to 7 mod 5, which is 2, and so that's what I've written here. This phi of 3 will send 7 to 2, and then similarly 6 plus 7x will send 6 to 6 mod 5, which is 1. 7, as we just said, goes to 2. The x goes to 3. And then if you add up all this, you get 7, which in mod 5 land is 2. So just as an example, 6 plus 7x under this unique homomorphism that sends x to 3 sends the 6 plus 7x to 2. So R join x is a polynomial ring in one variable. We can have more than one variable. So let R be a commutative ring. Then R join, for example, x, y, z denotes the commutative ring of polynomials in x, y, z with coefficients in R. Addition and multiplication are defined as in high school algebra. So because this is a commutative ring, I need x times y equaling y times x. And then the rules from algebra carry over to define multiplication and addition for more complicated polynomials. Like if I wanted to multiply out x squared plus y squared in this ring with z plus x, I just FOIL everything out, and there you have it. Again, because this is a commutative ring, we're insisting or declaring that, for example, x squared z equals z times x squared. You can also create a ring where you insist that the variables do not commute. That is such a thing, but I don't typically work with them, and I want to focus on these commutative rings. They're far more common, although certain fields of math definitely work with the non-commutative rings.